Chapter 4, Chemical Reactions and Chemical Quantities. So a chemical reaction is a process in which one or more substances are converted into different substances. So a chemical reaction occurs, or I should say when there's a chemical change, it is because a chemical reaction has occurred. So it involves chemical changes, like I just said, in matter resulting in new chemical substances, and chemical reactions are represented by chemical equations. So here is an example of a chemical equation right here. The way you read that is methane reacts with oxygen to produce carbon dioxide and water. The reactants are the things you start with, the things on the left. The products are the things you end with, the things on the right. That arrow separates them. That can be read as to produce. It can be read as yields, anything like that. Typically in chemical reactions, the states of all reactants and products are represented. So gas is represented by a lowercase g, liquid is represented by a lowercase l, solid is a lowercase s, and then water solution, aqueous, just means that something is dissolved in water. And so when an ionic compound is dissolved in water and reacting that way, it is called aqueous. And the water doesn't take part of the reaction when something is in aqueous solution. So looking at this equation here, CH4 plus O2 yields CO2 plus H2O. If we're looking for what is wrong with it, we see that I have I'm just giving it away. I have 4 hydrogens on the reactant side. I only have 2 hydrogens on the product side. I also have 2 oxygens on the reactant side, and I have 3 oxygens on the product side. So as it stands, this reaction is violating the law of conservation of mass, as explained here. So to make it not violate the law of conservation of mass, we have to do something called balancing the equation. When you balance, you use coefficients. Coefficients are written out in front. So like the 2O2 and the 2H2O. If there's nothing in front, the coefficient is 1. Technically, you can write it. If you want to, you don't have to write it. But you can see when it is balanced, I have 1 carbon on each side. Carbon is the black one. I have 4 hydrogens. Those are like the off-white ones. And then I have 4 oxygens. Those are the red ones on each side. When you are balancing, what I like to do is just list my elements under the arrow. It's a nice way to separate reactants from products. And as you can see here, I'm starting with 2 nitrogens and ending with 1. That's impossible. That nitrogen can't just stop existing. Same thing with the hydrogen. Hydrogen can't just start existing. That hydrogen had to come from somewhere. So to balance, the first thing I'm going to do is I'm going to put 2 in front of the NH3. And I do that because that will give me 2 nitrogens on my product side. That 2 tells me that now I have 2 nitrogens on the product side, but it also goes to the H. So I have 6 hydrogens on my product side. So now my nitrogens are good. I got 2 on each side, but my hydrogens are not. So I'll put a 3 on the reactant side to get 6 hydrogens on that side, and then that is balanced. This one was our example, but we'll walk through how to balance it. So this is called a combustion reaction, and one of the reasons they are a little bit more challenging to balance is because I have oxygen in the carbon dioxide and oxygen in water. So you're going to add those 2 together. 2 from the carbon dioxide plus 1 from the water gives me 3 oxygens. When you are balancing, you want to leave oxygen to the end. So my carbons are good. I'll balance my hydrogens by putting a 2 in front of the water. I put that 2 there because coefficients multiply. So 2 times 2 gives me 4 hydrogens on my product side. So now my carbons work, my hydrogens work. Oh, sorry, that 2 also goes to the oxygen. So now I have 2 oxygen on that side, or from the carbon dioxide, plus 2 oxygen from the water. I have 4 oxygen. So to balance my oxygen, I will put a 2 in front of the O2, giving me 4 on each side. This next one, just has phosphorus and oxygen. So probably you'd start by putting a 2 there to balance your phosphorus. But you have 2 oxygens on one side, you have 5 oxygens on the other. There's nothing I can put on that reactant side that's going to make that 5. We have to balance with whole numbers. So, little helpful trick, if you're stuck, you need to make odd numbers even. Easiest way to make odd numbers even is to double them. So then that will give me 10 oxygens. It will give me 4 phosphorus. So that's okay. I can erase that 2, change it to a 4, so I have 4 phosphorus on both sides. Put a 5 in front of the O2 to get 10 oxygens on both sides. So next one, we're back to another combustion reaction. So start with the carbons. Put a 2 there to balance my carbons. That's going to change my oxygens, but I'm not going to count them yet because I know I'm going to also do something with my water. So I'll put a son of a bee sting. Sorry about that. I'll put a 3 here to balance my water or my hydrogens, and that'll give me 6. Then I will have 4 oxygen from the carbon dioxide, and I'm going to have 3. That's an O, I swear. 3 oxygen from the water. So that's going to give me a total of 7. So I'm kind of in the same situation I was just in before, in that I have an odd number of oxygens on one side and an even number on the other. So in this case, we need to make the oxygens even. And what's going to make the oxygens even is this is kind of the odd oxygen here in the water, right? So we're going to change that. We're going to double that, just like we did in the other one, to 6. So now this is going to be 6 oxygens here. But when I did that, that's going to change hydrogens to 12. And so I would have to go back here and change the C2H6 so that I have 12. That changes my carbons to 4. So then I'll change the CO2 to balance my carbons. And then recount my oxygens. I have 8 from the carbon dioxide and 6 from the water. So that gives me 14. So I need a 7 in front of the O2. Oh my goodness. Okay. Writing the word equation and balancing. So solid potassium. And I'll just put that S to indicate if it's solid. If it's not given, you don't have to worry about it. But since it's given, we'll put it. Whenever an element's by itself, you need to check if it's diatomic. Diatomic is hydrogen, and then those 7 starts at 7, makes a 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Potassium is not one of them, so it is just K by itself. Reacts with liquid water to form gaseous hydrogen. Now, hydrogen is one of those diatomics. So it's by itself, it's just hydrogen, so it becomes H2 gas and potassium hydroxide. Now, when I put potassium hydroxide together, I'm still doing the same thing I did with naming, where potassium is a +1, hydroxide is a -1, so it's KOH. So in this one, oh, that dissolves in the water, sorry, it means aqueous. And then I have 1 potassium, I have 3 hydrogen, and I have 1 oxygen. Hydrogen because I have the H2 and the OH. So again, hydrogen's kind of the odd man out here. And what's causing it to be odd is that one in the potassium hydroxide. So first thing I'm going to do to balance this one, and this one's a little tricky, is I'm going to put that 2 there to make my hydrogens even. Now I have 4 hydrogens on that product side. It changes my potassiums to 2, it changes my oxygens to 2, but that's okay. I can fix that. So now that my hydrogens are evened out, I can change my potassiums and I can balance my hydrogens. And when I balance my hydrogens, the oxygens just kind of work out. Magnesium metal reacts with nitric acid. And again, nitric acid, I'm following the naming rules where no hydro tells me that there's oxygen in my formula. Ich is 8, so it's hydrogen plus nitrate. To form aqueous magnesium nitrate, so again, magnesium is a +2, nitrate's a -1, so it's magnesium nitrate's Mg and O3, 2. and hydrogen gas. Hydrogen by itself, so we check if it's diatomic. It is. Since it gave me the states, I'll put them in. It's really not going to make a difference. Now, this one, notice I have nitrate. I have NO3 on both sides. When you have a polyatomic ion that stays together on both sides, it is actually a little bit easier to balance it as one thing. So I'm not going to count nitrogens and oxygens separate. I'm going to count how many nitrates I have. You can do it separate if you want, but it is easier and faster to do it as one thing. So I have 1 magnesium, 1 hydrogen, 1 nitrate on my reactant side, 1 magnesium, 2 hydrogen, 2 nitrate on my product side. So I just need a 2 there in front of the nitric acid to make it balanced.